I want to take a little bit of time in the second video here of our radicals unit. You can look back at the first video. It will discuss mixed to entire and entire to mixed, and that becomes important when we try to add and subtract radicals. So what we're going to try to do in terms of adding and subtracting is find pairs of like radicals. So what does that mean? Well, radicals that are like radicals have the same stuff inside the radical. In other words, the radicands are the same, and it has the same index. Okay, so you can look at the little chart there, but pairs of like radicals are things like 5 root 7 and minus root 7, because the square root of 7 is the same in both, so you can add those together. However, 2 root 5 and 2 root 3, you can't add together. They're not like radicals, because it's root 5 and it's root 3. Here the radicand's the same, so you're allowed to put them together. Here the radicand is the same, but the root, the index, is different. So they're not like radicals. So it becomes very important when we add or subtract like radicals to know what it means to be a like radical. And in order to get like radicals, sometimes you have to convert from an entire radical to a mixed radical. So that's why we did that first in the previous video. So when you look at radicals, that's the one, first of all, that's the first thing you need to know is the idea of a like radical. But then you also have to understand something about even index radicals. And really the problem with even index radicals is that you can't have a radicand that's negative. Okay? It can't be negative. Now, it can be 0, but it has to either be 0 or positive. It can't be negative. And the reason is because you can't square something or take anything to a even power and get a negative number. So in other words, if I have minus 3 squared, that becomes 9. It doesn't become minus 9. So that means I can't take the square root of minus 9 because there is no square root of minus 9 in the real numbers. Okay? There is a complex number system that's outside the real number system that deals with negative square roots. But in the real numbers, you can't get a solution. So what we have to be careful of is whenever we have an even index, we have to correct for anytime there's a radicand that has an x inside of it. So if it's a number, no problem. But if it's a expression, then we have to do something about that. We have to state our restriction. Okay, so we have to say, for example, in this case, 4 minus x has to be greater than or equal to 0. And then we solve that and say then that x has to be less than or equal to 4. Okay, so you have to actually restrict your variable if there's a variable underneath a radical that has a positive even index. Okay, so that's sort of two just important points before we get into the actual operation of adding and subtracting. One is you have to have like radicals if you want to add or subtract them, and the second is you have to restrict even powered indexes. Okay, so we want to add or subtract these radicals. So what we're going to do, the first thing you're going to do in terms of steps or stages is you have to look at anything that is a radical and see, even if it's a mixed or entire, it doesn't matter, you look at the entire part of the mixed radical, so you look at this, or you look at just the whole entire radical, and you try as best you can to simplify that by writing them as mixed radicals in simplest form. So the square root of 50 I can write as the square root of 25 times 2. Okay, the square root of 2 I cannot reduce any further than it already is. Then this becomes, the square root of 25 is 5, so it becomes 5 root 2. This is still 3 root 2. Now that everything is simplified as best I can, I look and say, are there like radicals? Meaning, are there similar terms, different numbers in front maybe, but they have the same index, remember, and the same radicand, and they do here, root 2 and root 2. So I add them together, and I get 5 plus 3 is 8 root 2, and that's my answer. Okay, so when you're doing these questions, you have to simplify first. That's why, again, in the first video, we talk about converting between mixed and entire radicals. So if we look at question B, we have minus root 27. I'm going to write that as 9 times 3. 3 root 5, I can't do anything with that. Minus, and then I'm going to write 16 times 5. That's what 80 is. And minus 2 times, and then 4 times 3. Okay, this is a unique one because it's already a mixed radical, but it's not a mixed radical in simplest form. So even though it's already a mixed radical, it's not enough to just say, well, it's a mixed radical, so I'll leave it as root 12. You have to look at the root 12 and recognize that it can get even smaller. Okay, then we do the square root of 9 is 3. So we get 3 root 3, then plus 3 root 5, then minus square root of 16 is 4 root 5. And then this becomes, and this is a little bit different, when you take the square root of 4, you get 2, but it's going to get multiplied by this 2 that's already there. So this is going to become 4 root 3. Okay? And then what we're going to do is we're going to put them together in terms of the like radicals. So there's a root 3 and a root 3. So we put those together and get minus 7 root 3. And then we have a root 5 here and a root 5 here. 3 minus 4 is minus 1, so minus root 5. And that is our answer. Okay, so that's how we do those questions. And then if you look at part C, I'm just going to erase this. The solutions are actually down here as well. Okay, so you don't have to worry about having them written down. If you look at part C, we're going to start with square root of 4c, so that's going to be 2 root c. Okay, we don't have to actually simplify in terms of writing that as a perfect square because it already is, but we have to write the square root part out. So the square root of 4 is 2, so we get 2 root c minus, and then the square root of 9 is 3, so this becomes 12 root c. And then 2 root c minus 12 root c is minus 10 root c. Okay, and that's my answer. And then you'll notice this has a restriction. And the reason this has a restriction is because there's a variable that's underneath the radical sign, and it's an even index. So you have to restrict the root. So there's our solutions. And then there's a your turn. You can try these 3, okay, and then see what you come up with. And again, check your answers with your teacher. There's more practice here. We'll just pick a couple of these. Make this just a little bit bigger so you can see it. If you look at this very first one, these ones are pretty straightforward. 5 root 3 plus root 3 is 6 root 3. Okay, 6 root 7 minus 3 root 7, those are like terms, so we just subtract, so we get 3 root 7. So those are pretty simple. This one, you have root 2 and root 2, so 6 minus 1 is 5 root 2. And then 3 root 5 plus root 5 is 4 root 5. Okay, and then this guy, we have 4 root 10 plus root 10, that's 5 root 10. And then we have minus 3 root 6 minus root 6, so that's minus 4 root 6. Okay, when you get it down here, we'll just do these two. Then you have to start trying to find perfect square factors of these. So root 90 is root 9 times 10. I'm going to split this into 16 times 10. And then the square root of 24, we're going to write it as 4 times 6. Okay, so then this becomes 3 root 10 minus 4 root 10, and then plus 2 root 6. And then 3 root 10 minus 4 root 10 becomes minus root 10 plus 2 root 6. I can't put the 2 root 6 and the root 10 together, so I leave it like this. Okay, so there's more for you to practice with there, and you can sort of see if you can get your answer. And what you can do, if you want to check your answer, is just type this into your calculator, see what it gives you, in other words, what you started with, and then type in your answer, your simplified answer, and see if it gives you the same decimal. It will be a decimal most of the time, unless it's a nice square root, but generally, if it's a nice square root, we're going to take the square root, right? So your answers are probably going to be just irrational numbers, but you can check your answer that way if you're not sure if you did it right. So I'll leave the other ones there for you to practice. We don't need to go through every single one of them, but that's the idea. Now, these are all square roots. Okay, if we look at some of the other things, you could do the same thing with cube roots. The problem with fourth roots and cube roots is that you just it's harder to find the answers. In terms of the perfect squares, perfect cubes are a little bit bigger, perfect fourths are even bigger. So that's the issue. But if you look at practicing these, I think it'll become pretty easy. And multiplying and dividing are different than this. So you should practice your adding and subtracting first, okay, and then we'll get into multiplying and dividing. However, I am going to cover all 4 of the ratios, or the operations, sorry, in this video. So we're going to do multiplying next. When you look at multiplying, basically what happens when multiplying is the only thing that has to be the same is the index. So you have to have the same index in order to multiply. And then what you do is you multiply the numbers, if it's a mixed radical, the numbers outside the radical sign. So in this case, 2 root 7 times 4 root 75 becomes 2 times 4, and then square root of 7 times 75, okay? And then you would multiply the 2 by 4 to get 8, and the 7 by 75 to get 525, and then you simplify that as best you can, all right? Now the other option, which you'll see down here, is you can simplify the radical first. So you can notice that square root of 75 is actually the square root of 25 times 3, which gives you 5 root 3, which then becomes 4 times 5 is 20. So you get 2 root 7 times 20 root 3. And then when you multiply those, you don't have to simplify after the fact. So the difference is really where you want to simplify. Do you want to simplify before you multiply, or do you want to simplify after you multiply? Okay, but that's the idea of multiplication. Pretty straightforward. Okay, so in general, if you have 2 radicals, it's the numbers in front multiplied together, and then the root sign, and then the numbers underneath the radical signs. So let's look at a few examples just to sort of show you how this works. Again, you'll notice some have restrictions, and it's because of what we talked about earlier. So we have an x underneath this radical sign, so we say x has to be greater than or equal to 0. But then we just multiply. So 3 times 4 is 12, so we get minus 12. And then it's the square root of, and then 6 times 2 is 12x. And then we try to simplify the 12 if we can, which it's a square root, so it has a perfect square factor of 4 times 3x. And then you take the square root of 4 and you get 2, so you get minus 24 square root of 3x. Okay, there's my answer. Here, when we're multiplying these, its multiplication is very similar to polynomial multiplication. So when you're multiplying, you're going to multiply that by that, and then this by this. So 7 root 3 times 5 root 5, you go 7 times 5, so that's 35, square root of, and then 3 times 5, which is 15. Okay, then minus 6 times 7 is 42, and then root 3 times root 3 is root 9. Okay, then we try to simplify. So 35 root 15 doesn't simplify. There's no perfect square factor of 15. However, 42 times the square root of 9 becomes 42 times 3. The square root of 9 is 3. So you get 35 root 15, and then minus 42 times 3 is just 120 plus 6, so it's 126. Okay, and again, your solutions are here. They're listed down below. So I'm not going to go through every one of these, but when you multiply, again, you're multiplying, in this case, 8 root 2 and 9 root 5. You're going to multiply 8 by 9 to get 72, and then root 10. The only difference here is, and I'll show you this one just down with the solution, is you've got a binomial times a binomial. So you're going to do it the same way you would have with polynomials. You're going to multiply the first terms together. Okay, so 8 root 2 times 9 root 5. Then you're going to multiply 8 root 2 by 6 root 10. Then minus 5 by 9 root 5. And then finally minus 5 by 6 root 10. You're going to use the distributive property. You may have heard it called FOIL. First outside, inside, last is a kind of quick way to remember it. And then what you're going to do is you're going to actually multiply each of these out. So we get 72 root 10. Here we get 48 root 20. Then we get 45 root 5. And then finally 30 root 10. And then we try to simplify. This guy, root 20, will simplify into a mixed radical because you have a perfect square factor. So the square root of 4 times 5. Then the square root of 4 is 2. 2 times 48, is 96 root 5. And then what you'll notice is we have two sets of like terms. We have 72 root 10 minus 30 root 10, and we have 96 root 5 minus 45 root 5. And so we end up with that as our answer. So very similar. Each of these is kind of similar to polynomials. If you remember your polynomials and working with x's and x squareds and that sort of thing, and it's pretty much the same idea. Your like radicals are kind of like your like terms of polynomials. It's just that instead of the x's having to be the same or the x squareds, it's the radicands and the radical indexes that have to be the same. But it's pretty straightforward as long as you use your multiplication from polynomials, the same idea, and you use your knowledge of converting radicals from entire radicals to mixed radicals and simplifying, and then you use the addition and subtraction that we talked about just prior to multiplication. So it kind of builds on itself. It's mixed and entire radicals first because you need to be able to simplify those in order to add them properly, and you also need to be able to simplify them in order to multiply them properly. And then once you've multiplied, sometimes you have to then add or subtract afterwards. Okay? So there's another, that's the last example. And again, you're going as a cube root. But if you look at this, again, we would go 9 times the cube root of 2w times the cube root of 4w. So the 2w and the 4w get multiplied together. And then you do 9 times this guy. 9 times 7 is 63. And we get 2w times 28. So we get this. And then we take and simplify those if we can. So we're looking for a perfect cube. So 8 is a perfect cube, right? It's the cube root of 8 is 2, so we get 9 times 2 on the outside of that. And then 56 has a perfect cube also of 8 because it's 8 times 7. So then we take the 2 out, the cube root of 8 being 2, and that's where we get that 126. Okay, it's 63 times 2. And what's left, 56 is 8 times 7. If you want to write that there, because it doesn't really indicate what we're doing, we're writing it as 8 times 7w. And then the cube root of 8 is 2, so it's coming out front. Okay, so that's the idea. And again, here's some for you to try. It's all these are all multiplication, different types of multiplication, but that's the idea behind multiplying. You've seen 4 examples now, or a few more than that actually in the video. So hopefully you can sort of determine what these answers are on your own. Now, the last operation is division. Okay, so when you're dividing, as long as the radicands have the same, the radicals, not the radicands, the radicals have the same index, then you can just divide the radicands. So you have, in this case, 4 cube root of 6 divided by 2 cube root of 3. All you do is divide the 4 by 2 and get 2, and 6 divided by 3 is 2. Okay, so it's pretty simple if it's a single division. All right, so if you're just dividing something by one monomial radical, then it's pretty easy. So here's another example. So here's what we do. We take the square root, because that's the radical. When you divide 24 by 3, you get 8. And then x squared divided by x is x. And then we simplify if we can. So we get the square root of 4 times 2x, and that becomes 2 root 2x. Okay? And that's our answer. So that's the idea of division. Okay, and there's a bunch of practices here that you can try. There's a whole bunch of questions to try, whole bunch of multiplications, and this practice will be posted for you. But let's just look at a couple of these divisions. Let's look at this one here. I'm just going to pull it out over here. And if you look at this, it's the cube root of 30 divided by the cube root of 5. So I'm going to do that first. I'm just going to look at this and do this. So 30 divided by 5. And I'm going to say, what's 30 divided by 5? Well, 30 divided by 5 is 6. Then we're going to have the cube root of 6 and the cube root of 20 divided by the cube root of 3. Okay, so I'm going to then divide 6 by 3 and get the cube root of 2 times the cube root of 20. And that gives me the cube root of 40. Okay, and then the cube root of 40 I can simplify because 40 has a perfect cube factor. So we get this, 2 cube root of 5. That's my answer. Okay, so that's kind of the idea behind division. Now, there is one more thing about division, and it's what happens if you divide by something that's actually a binomial, as two terms. But we're going to just stick with division practice of one term for now until we get down to these questions. Okay, and that has to do with what is called rationalizing the denominator, and you have to multiply by the conjugate. So we're going to leave these here for you. They're pretty straightforward, but the question is, what do I do with something like this? What do I do with these? Okay, so that's going to be the final part of our video, and it has to do with rationalizing the denominator. And when you rationalize the denominator, essentially what you do is you look to divide first, but if you can't, then you try to just get rid of the radical in the denominator. So rationalizing means we're taking it from a non-rational number to a rational number. We're trying to make an irrational number rational. Okay, and what that means is we need to get rid of the square root. So if you look at this, the first thing we would try to do is divide, but 2 doesn't divide by 3 nicely. It gives us 2/3, right? So what we do instead of actually writing this as the square root of 2/3 is we write in multiply by root 3 on the top and the bottom. Okay, and then the top becomes root 6 and the bottom just becomes 3 because root 3 times root 3 is root 9, which is 3. So we leave it like this. Okay, and it's called rationalizing the denominator because now instead of the denominator having a radical sign in it, it doesn't. Okay, it's just a rational number. It's 3. That's the idea of rationalizing the denominator. Now, if you have two terms, going back to the previous slide where I said, what do we do with these two terms? Then what you do is you multiply by the conjugate. So what's the conjugate? Well, the conjugate is same terms, okay, exactly the same terms, but the opposite sign in the middle. And what we're doing is we're setting up a difference of squares. Okay, so you probably know by now, we did talk about this, that a perfect square goes like this. It factors as a minus b, sorry, not a perfect square, a difference of squares. It factors as a squared minus b squared, factors as a minus b times a plus b. So what we're doing is if we have this part, then we want this part, right? In order to get a squared minus b squared, because what that's going to do is it's going to actually square both of these, okay? So to show you that, we're going to multiply by the square root of 2 plus 4 on the top and the square root of plus 4 in the bottom, or the denominator. When we do that, the top is going to become root 6 plus 4 root 3, right? Because we're multiplying root 3 by root 2 and then root 3 by 4. And the bottom, all we do is we square the 2, so it becomes 2, and we square the 4, and it becomes 16. So what we then end up with is the square root of 6 plus 4 root 3 divided by minus 12. Okay? Sorry, minus 14, not minus 12. And then all you do from there is, if you can, you simplify the numbers, but the coefficient here is 1, the coefficient there is 4, so you can't divide anything. Like 4 and 14 reduce, for example, by 2, but you can't because there's not a 2 here. So you just leave it like this. And you can, if you want to, if you don't like the negative being down in the denominator, you can write it in the front of the fraction. But that's the idea behind multiplying by a conjugate. So if we jump back here for a second, here's an example where we have root 5 divided by root 3. We say we can't divide that nicely, so we're going to just multiply by root 3 over root 3. So that gives me root 15 divided by 3. Okay? Here, same thing. We can't divide this, so we're going to multiply by root 3 on the top and the bottom. When we do that, we get root 6 on the top and 2 times 3 on the bottom. Notice I didn't multiply by 2 root 3. I don't need to do that. I just leave it alone. Okay? And then that becomes root 6 over 6. So that's what we mean by rationalizing the denominator. So some of these are going to divide nicely, okay? And some of them don't. So if they don't, then you want to do that. And if they don't, but they reduce, then you can do that too. Like the square root of 8 over 100 becomes this, right? You can divide them both by 2. And then that becomes 2 over 5, okay? Or you can sort of write this, I guess, if you want to instead, as this first, and then reduce to 2 over 25. That's root 2 over 5. Okay, we're dividing both by 4. So you can get root 2 over 5 that way. So in other words, I don't need to rationalize the denominator right away because it does reduce, but it doesn't give me a nice number. Some of these also, if you look at this one, for example, you have 3 over 2 times, and then 20 over 4 becomes root 5. And you just leave it like that. So you try to divide or reduce if you can. If you can't, or once you get to the point where you can't, you rationalize. If you can't do that because you have a binomial on the bottom, you're going to multiply by the conjugate. We'll look at a couple of examples of that, which we're going to multiply in this case by the conjugate. So that means we multiply by 4 minus 4 root 5. And again, you identify that. The reason I went back to these questions first is to show you try to simplify as much as you can. If you can't simplify or things don't divide nicely, then you rationalize. And that means if you're left with a square root on the bottom, you multiply by the square root of whatever's on the bottom, and that rationalizes the denominator. If you end up in a situation where you have a binomial, then you automatically have to multiply by the conjugate. Okay, so we're going to do that. So 3 times 4 is 12, minus 12 root 5. And then on the bottom, we square these. So we get 16 minus 16 times 5. Okay, so that gives me 12 onto 1 minus root 5. If I just take the 12 out of there, and this gives me 16 times 1 minus 5. Okay, you might be saying, why are you doing that? Well, 12 over 16 reduces to 3 over 4. And then this becomes minus 4. So you end up with 3 times 1 minus root 5. And then all divided by 4 times minus 4, which is minus 16. So there's my answer. Okay, that's my multiplication by the conjugate. And you can do that with any of these. I'm not going to do every single one, but let's look at this one. We have root 2 minus 5 root 3. So again, we're going to multiply by the conjugate. That's root 2 plus 5 root 3. And this becomes root 2 plus 5 root 3. If you multiply, then you get 4 root 2 plus 20 root 3 on the top. On the bottom, you end up with 2, because you square that term, and then minus 25 times 3. Okay, so that gives me 4 root 2 plus 20 root 3, and then divided by 2 minus 75. So that gives me minus 73. And that's my answer. Okay, so you can try some of these on your own as you go through, but you end up multiplying by the conjugate anytime you have this binomial on the bottom. And what ends up happening, the purpose of that is to rationalize the denominator. So what ends up happening is you get a number on the bottom, a rational number. Okay, so it's important that you actually end up with that. If you didn't, when you did this, if you do a question and you don't end up with a number here, if you still have a square root in the denominator, you did something wrong. Okay, so that's the concept of rationalizing the denominator. And then there's more practice here as well. And then what we're going to do, the last part of this in the last video we'll do is radical equations, solving radical equations. So we'll leave it there for now. There's some more questions there for you to try, and you'll get the solutions from your teacher if you want them. But we'll leave it there, and then we'll pick up on the last video. We'll do the solution to radical equations.